Welcome to the theoretical computer science at Jagiellonian University. Our speaker today is Sophie Spirkl from the University of Waterloo. Sophie is an assistant professor at Waterloo. She did her PhD in Princeton under the supervision of Maria Czudnowski and Paul Seymour. She is very well known for her numerous results in structural graph theory concerning chi-boundedness, polynomial chi-boundedness, induced subgraphs, tree decompositions, and this is going to be also the topic of today's talk, induced subgraphs and treewidth.
All right, should I start?
Yes, please.
Okay, thank you so much. Thank you for the introduction and thank you for inviting me. Thanks everyone for coming. So I will tell you about a result about induced subgraphs and treewidth, and I'm happy to have questions from you at any time. I will see them if they're in the chat, or I don't know how the seminar usually does it, but I'm also happy for you to unmute and just ask. At any point. So yeah, this is a result which is joined with Tara Abrashami, Bogdan Eleku, Maria Czudnowski, and Seper Hashabi. And it's on treewidth. And so I assume many people here know what treewidth is, but also for each of these talks, I have to tell you what treewidth is, and I have to tell you in the first 10 minutes. So let's see if I can tell you a sensible level of detail about what treewidth is in 10 minutes. So treewidth measures complexity of a graph, and in particular, it measures in some sense how much a graph is like a tree. And treewidth was used by Robertson and Seymour as one of the main ingredients of the graph minor series. And here's a picture where I drew a graph, and then I drew a tree that looks sort of like it. And then there's a thing in the middle, which is very colorful, but perhaps not very illuminating at the moment. So I'm going to show you the definition of treewidth, and then we'll come back to this slide and see where that definition and this slide actually show the same thing. So the plan for tree decomposition is you have any graph G, and then we're going to take a tree T, and this is not a tree in G, this is just a tree that is separate. And we're going to associate to each vertex of a tree T some subset of the vertex set of G. And these subsets are called bangs of the tree decomposition. So any tree T, each vertex of T corresponds to a subset of the vertex set of G and is called a bang. And then this doesn't tell us anything about the graph yet, so we need to say something about how the edges of the graph intersect with the structure. And that's the statement. Every edge is contained in some bang. Every edge of the graph is contained in some bang. And then there's one more condition, and this might be, if this is your first time seeing tree decompositions, a kind of mysterious one, because it's not clear how this does something helpful. But it says for every vertex of the graph, I look at a vertex of G and I ask in T, which bangs is this vertex in? Then there should be a non-empty set of bangs. So every vertex should be in some bang. And moreover, for every vertex, the bangs that it's in should make a connected subtree, which this makes sense, for example, because otherwise you could do a tree decomposition where you just do any tree, and then for each edge you give it its own bang. And again, you have learned absolutely nothing about the structure of G. But this condition, as it turns out, makes it so that a tree decomposition says something meaningful. And here, going back to the picture, this is the graph, so this is G, and this is a picture of T. And I've used all the colors that I could find in this program to give each vertex a different color. And then over here in G, I've drawn these blobs that show subsets of the vertex set that correspond to a given vertex in T. So for this T1, which is red, we have this subset, right? These three vertices of G. And for this vertex T2, we have this orange set. And now you can see we've met the second condition. Every edge is in some bang, because for every edge of the graph, you can see there's one of these colorful blobs. My computer is giving me trouble. For the third condition, let's look at the vertex of the graph, for example, this one. And we can see that it's in 4 bangs: brown, dark blue, orange, and pink. And brown, dark blue, orange, and pink form a connected subtree. So this is a tree decomposition, and this is how it works. And tree decompositions are useful in a number of ways. One way they're very useful is for algorithms. Anything you can think of that you can do in a tree using dynamic programming, almost always you will also be able to do in a tree decomposition using the same dynamic programming strategy, because it tells you that the graph really is organized like the tree, and in particular, where you would expect non-edges and cut sets in the tree, you get similar things in the graph. And now, when you think about it, it's easy to make a tree decomposition of a graph. You could just make T have one vertex and put all the vertices in that bang. So tree decompositions where bangs are big are easy, but the part we like, where it actually says something, right, with something that might also help for dynamic programming, is if bangs are small. And so the width of a tree decomposition is the maximum bang size plus a very annoying -1. And the point of this -1 is that the tree width of a tree is 1. But now we all have to remember that there's a -1 here. So the width of a tree decomposition is the maximum bang size, and the tree width of a graph is then the minimum width of a tree decomposition. So this thing shows us that for the graph I've drawn here, we have a decomposition where each bang has at most 3 vertices. So the tree width of this graph is at most 2. And so now the question then we're after is, right, if graphs have small tree width, we like them for algorithms, for structure, and so on. And so what causes large tree width, right? What things do we need to exclude for a graph to say, and now it has small tree width? Which graphs have large tree width? What is their structure? And as I told you, Robertson and Seymour studied those as part of graph minors. And in the graph minors universe, they gave a complete answer, which is a graph has large tree width if and only if it contains a large wall as a minor. Where a wall is this thing, right? It's a thing that looks as though you were building a brick wall. And to make a wall bigger, you can give it more rows and then also more bricks per row. And large tree width means you have a large wall, and conversely, a large wall has large tree width. So in this sense, we understand exactly what causes large tree width in the graph minor setting. And also, there's a standard result for minors, right? A wall is a graph of max degree 3, and for those containing it as a minor is the same as containing a subdivision of it as a subgraph, which means if we go to just subgraphs, we still know the answer. Large tree width means having a subdivision of a large wall, and subdivisions of large walls have large tree width. And so these questions are all solved, and it's a very beautiful answer. And what I want to talk about is, what about induced subgraphs? So for induced subgraphs, right, as probably all are aware, but I still say this in every talk, the rule is that you're allowed to delete vertices, but not edges. So the only way you delete an edge is if you delete one of the vertices incident with it. And then something like this is no longer true, right? Because, for example, a complete graph contains a large wall as a subgraph, but not as an induced subgraph. So in the induced subgraph world, we can now still ask, suppose a graph has large tree width. Can we tell that it contains one of these 10 kinds of induced subgraphs of large tree width? And so what are natural candidates for this? Well, still walls, right? If I look at walls and their subdivisions, where subdivision means I take an edge, I turn it into a path, and possibly I do that for all edges. And then these are still graphs of large tree width, and they are only induced subgraphs that have large tree width are also subdivisions of walls. So one of the families of graphs that we should exclude if we want to say forbidding this gives a small tree width are walls. And there's another class that looks exactly like a wall, except we replace each of these places where three edges meet by a triangle. And this is the line graph of a wall. And like a wall, it has large tree width. And neither of these pictures contains the other, right? Because over here, we do not have triangles. But over here, we don't have claws. We don't have a vertex with three neighbors that are non-adjacent. So in the induced subgraph world, walls don't contain line graphs of walls, and line graphs of walls don't contain walls. So these are already two families of graphs that we should exclude if we want to get small tree width. And then we already said the complete graphs are a problem, right? Complete graphs have large tree width, for example, because a large complete graph contains a large wall as a subgraph. And all their induced subgraphs are also complete graphs. So again, in our collection of which graphs could cause large tree width, complete graphs should make an appearance. And the same for complete bipartite graphs. Again, it's not hard to see they have large tree width. And on the other hand, every induced subgraph of a complete bipartite graph is a complete bipartite graph. So that's four types, right? We need to exclude subdivisions of walls, their line graphs, complete graphs, and complete bipartite graphs. And could it be that this is the truth, that this is everything? We will see that later, but first I want to show you this, which is a beautiful result due to Lawson and Razgon, and a complete answer if I exclude finitely many graphs, right? If you look at walls, we need to exclude all subdivisions of a thing, and that's infinitely many things. But if I want to ask, here's some finite set of graphs, exclude all of these, so that not containing these as an induced subgraph gives you bounded tree width. For this question, Lawson and Razgon have a complete answer. Right, we want to say which induced subgraph should I exclude to get bounded tree width. And if we exclude infinitely many graphs, it's not clear. We've shown you we need to get rid of those four kinds of things. But if I exclude finitely many things, here's a complete answer, which things will give bounded tree width. And for a finite family of graphs, we still need to exclude a complete graph. We still need to exclude a bipartite graph. And then to get rid of walls, we need to exclude a finite family that is contained in all walls. And so we have to exclude a tripod, which is a forest, meaning a disjoint union of trees. And each of them has at most 3 leaves. And this makes sense somehow, because if you think of a wall and think of subdividing it a bunch of times, then all its degree 3 vertices are really far apart. So if we exclude a finite family, we can subdivide it so much that no graph in our family contains two vertices of degree 3 in the same component. So our only option is that each component only has one vertex of degree at least 3, and likewise we can subdivide it so much that no graph in our family can contain a whole of a wall, and therefore it should be a forest. So tripods kind of think of, these are the finite families of graphs that kill large enough walls, right? To get rid of large enough walls, as a counterexample to this, we need to exclude tripods. And then you can imagine their line graphs, which basically means replace each degree 3 vertex and its neighbors by a triangle. Right, so this is the line graph of that. And we need line graphs of tripods precisely for what you might expect, to get rid of line graphs of walls. So this is a beautiful result, and it kind of gives some hope, right? That these four families that we talked about, walls, their line graphs, complete bipartite, are maybe just the four kinds of things that can cause large tree width, because excluding a finite set of things comes down to exactly excluding a finite set of things that kills off each of these four families. And so from now on, we'll exclude infinitely many things, and we'll try to exclude something from all the families. More precisely, if I have any graph and it has large tree width and it contains one of these of reasonably large tree width, I will say, well, that's a good reason that graph has large tree width. So let me instead look at graphs that are T-clean, meaning they don't contain any graph of this form of tree width at least T. And so then, right, it would be lovely if it was true that T-clean graphs have bounded tree width in terms of T. And this is sort of analogous to the graph minor thing, where if we don't contain a graph of this form as a minor, we have bounded tree width. So could it be true that if we don't contain any of these things as induced subgraphs, tree width is bounded? And here's another result that gives us some hope. This is due to Korhonen, and it's fairly recent, and again, a really beautiful result. And this says, you know, all the things we hope to be true. If I tell you that maximum degree is bounded, then they are true. So what does that mean? Well, if maximum degree is bounded, then I don't contain large complete graphs and also don't contain large complete bipartite graphs. So if bounded maximum degree is true for a graph G, then I've already automatically excluded two of the graphs in my family of basic obstructions. So the only additional things I should exclude are walls and their line graphs. And Korhonen proves that if we have large tree width and bounded maximum degree, then we contain a large subdivided wall or its line graph as an induced subgraph. And this was conjectured by Abulke, Adler, Kim, Cintiari, and Trottineau. And many people, I think, worked on it very hard. And then Korhonen gave a proof that, at least surprisingly to me, was quite short. So I actually want to tell you a few words about how this proof works, because it's a really beautiful result, but it actually doesn't take long. And the idea is this, and let me know if you can't hear me intermittently because my computer is adversarial this morning. So the idea is we partition the graph into stable sets. And we can partition the graph into a few stable sets where two vertices in the stable set are pairwise far apart. Because the graph has bounded degrees, so for each vertex, what I can reach in 5 steps is still a bounded number of vertices. So that graph can be partitioned into a few stable sets that cover the whole graph. And then for each stable set in turn, right, there are a constant number of them. And for each in turn, we want to clean up vertices in that stable set. And to do that, we contract for each vertex in Si a ball of radius 2 around that vertex, which is fair because in Si vertices have distance 5, and so their balls of radius 2 don't contain vertices in common. So we contract these. What does that do to tree width? It actually only changes tree width by a constant factor because we contract bounded size things. And so if we take a tree decomposition and then uncontract, each band only becomes bigger by a factor that's the size of the things we've contracted. So in that graph, having contracted balls of radius 2, we should have a large wall as a subgraph by the Robertson-Seymour result. But in that wall, for each vertex, there were only 3 of its neighbors that we cared about, right? Each of these vertices in a wall subgraph has only 3 neighbors that are in the wall. So if we uncontract, for each vertex, there are only 3 or possibly fewer of its second neighbors that we care about in order to have this wall. And so all we want is that this wall subgraph still exists after uncontracting. So we can throw out everything that has distance at most 2 from vertex V, except these 3 vertices, and then some way to connect them within the ball of radius 2 around V. And thinking about it for a minute, the ways to connect 3 vertices in this ball of radius 2 are only the 2 pictures here, right? If I just get a minimal thing that connects these 3, it's the 2 things in the pictures. Or it could be other things that don't involve V. But after this step, we throw out everything at distance at most 2 from V except whatever's here, the stuff that's really important. And so for each vertex in Si, after this step, we might have thrown it out, but if it's still there, then its neighbors look like one of these things. And those first neighbors don't have any other neighbors except what's drawn here. And we only change tree width right through all of these a little bit. If it was big before, it's still big after. And so doing this process, we then arrange that every vertex has a neighborhood that looks like this, and in fact, a second neighborhood that looks like this, and tree width is still large. And now just taking a wall subgraph gives you an induced wall, because any extra edge would give rise to a vertex whose second neighborhood doesn't look like the picture. This was a very quick description of this proof, right? And I've certainly glossed over a lot of details, but it's really pretty that we can clean up kind of for each vertex just the stuff really close to it without hurting tree width too much. And then once every vertex looks like this, a wall subgraph is just an induced wall. All right, so far we've kind of built up your hopes, right? I've showed you 4 families of forbidden things and then 2 beautiful theorems that support the conjecture that these 4 are a complete answer to what causes large tree width, right? Both in graphs of bounded degree, and if we exclude only a finite family of stuff, it looks like those 4 might really be the answer. And they are not. So this is a picture that I've used in a few talks because it took me forever to draw. And so I am getting maximum mileage out of it. It's a construction due to Centauri and Trottium. And before telling you the details of it, let me tell you why it's interesting. It has large tree width. It doesn't contain a triangle, which means in particular, no large complete graph, no line graphs of walls. It doesn't contain this thing, which that's a K23 and all its subdivisions. It doesn't contain this as an induced subgraph, which means it doesn't contain large walls. And also, if you just subdivide each, right, if you just have one vertex in each of this, that's a complete bipartite graph. So it also doesn't contain large tree width complete bipartite graphs. In other words, this construction doesn't contain basic obstructions of large tree width. This is T clean when T is at least, let me be, let me say 4, but probably less. So this is 4 clean and still has large tree width, and so shows that the 4 families of things are not enough. And this construction is recursive. We have one vertex, and then we construct a new path according to certain rules, giving vertices on the previous path neighbors. And which neighbors we give depends on having neighbors up or down. So this vertex has a neighbor up. And so we do a certain thing on the next path. This doesn't have a neighbor up. We do a certain thing, and it grows exponentially from there on out, which is why I've only drawn 2 and like a 5th layers. But it's a really nice construction that disproves lots of things. It also shows that Cohonen's result is in some sense optimal, because this vertex, if you sort of extrapolate based on the incomplete information I gave you, this vertex will get larger and larger degree as we continue. And so this has unbounded degree. All right, so what do we make of this? Right, this also looks like it's just one graph, but actually it's a family of graphs. There are several places where you have kind of a few choices of what you can do. And so it's not sensible to say, all right, this is number 5. And now if we exclude these 5 families, maybe everything will be true, because this is not just one family. There's some amount of choice we have here. And so what I want to show you is a strengthening of the Lawson and Rasgon result, but also kind of building on a lot of their techniques, where I'm going to say, let's exclude the basic obstructions, right? Exclude the 4 usual suspects that we've talked about for a while. And then I will exclude only one more graph. Which choice of one more graph will give us bounded tree width? And the answer will be a subdivided star forest, which a subdivided star forest looks like this. In other words, it's a forest, and each component has at most one vertex of degree more than 2. So, right, each component will have a root which has degree more than 2, or maybe all vertices have degree of most 2. And then from this, a bunch of paths coming out of it. And we saw that T-clean graphs don't have bounded tree width, but our main result is that H-free T-clean graphs have bounded tree width if and only if H looks like this. And H-free means it doesn't contain H as an induced subgraph. So, right, Lawson and Rasgon told us if we exclude finitely many things, here's what they look like. And this result says, I will exclude infinitely many things of the basic obstructions, right? I will exclude all walls of site, all subdivisions of T by T walls and their line graphs. But then I'm only going to exclude one more graph. Which choice of one more graph will give bounded tree width? And it will turn out it is only these. And I will actually, I think, show you the complete proof subject to one lemma about treewidth. And so first, let's start with why, right, this is if and only if, and there's one direction where we should show that if H is anything other than this, then H-free T-clean graphs don't have bounded treewidth. And so for that, I will show you another example of T-clean graphs of unbounded treewidth, and this one is due to Davies. And it looks like this, which means we have some number of paths and then some number of vertices that have neighbors in all paths. And if I have both a lot of paths and a lot of vertices with neighbors in all paths, then treewidth is large. But also, if we look at this, most of these, right, except for at the very ends, these vertices have the property that deleting it and its neighbors disconnects everything. They're star cut sets, which is not a thing that happens in a large wall or its line graph. And this is my very short and somewhat imprecise attempt to convince you that these things don't contain walls or their line graphs. Right, and walls or their line graphs, for each vertex, if I delete it and its neighbors, not much happens. But here, for these vertices, if I delete it and its neighbors, things actually break in half. And so having a wall in here is impossible. And, you know, this has been said more carefully, but this is somehow the intuitive reason why it's true. And they have large treewidth, and they still have large degrees, so they're not a counterexample to coordinates theorem, because these degrees grow large as treewidth grows. And on the other hand, we can make these paths, I just drew one vertex in between, but we can make them very long. And so we can make it so that they don't contain short cycles, right? So if H is one graph that we exclude on top of the basic obstructions, it should be contained in this, even if we subdivide the paths a bunch, which means H better be a forest. Because if we subdivide in all these places a bunch of times, then each cycle is very long and therefore contains more vertices than whichever H we were thinking about. Right, does that make sense? So this shows if we exclude basic obstructions, treewidth is not bounded. If we only exclude one more graph, it should be contained in all of these things, but then it should be a forest. And now let me make a tiny modification. So now instead of giving each vertex one neighbor on each path, I'm giving it two consecutive neighbors. And then again, thinking about our favorite graph H, which we now know is a forest, if I subdivide in each of these places a lot, then no component of H contains two of the colorful vertices because they are far apart. And at each colorful vertex, if we go to any path, we don't contain both of its neighbors on that path because H is a forest. So from each of these vertices, we only contain a path, possibly in a bunch of different directions, right? This shows vertices of H of degree more than 2 live in different components of H, because the only vertices of H that could have big degree in H are the colorful ones, and they are too far apart to be in the same component of H. So far, with any luck, I have convinced you that I can never do this when I'm put on the spot, but I think I've convinced you of the only F direction, because these are both T-clean graphs, and if we want one finite graph H that's contained in both of these constructions, it should be a star forest. So now let's do the other direction. Let's prove if we exclude the basic obstructions and in addition some star forest, then tree width is bounded. And so in the rest of the talk, I will tell you the proof. And I think it has a lot of pretty steps, but none of them are nearly as much work as we've done up to this point. So hopefully, this will be kind of a nice and not too hard part of it. So from now on, I'm excluding H, some subdivided star forest, and I'm also assuming that G is T clean, meaning it doesn't contain a basic obstruction of tree width T. And if you look at a star forest, right, it has a lot of components, but by making H a bit bigger, I can assume that all these components are isomorphic to the same subdivided star F, right? By just taking one component, which is so big that it contains each other component as an induced subgraph, and then taking a bunch of copies of that, and can assume each component of H looks the same. And excluding this, I want to show tree width is bounded. So we'll start by showing that we can delete a few vertices, and instead of being H-free, we can actually become F-free. And deleting a few vertices decreases tree width a bit, but not a lot. Right, deleting K vertices decreases tree width by at most K. And then we will show that T-clean F-free graphs don't have a K block, which is a certain highly connected set. And after that, we will show that T-clean graphs with no K block have bounded tree width. So first, let's reduce from H-free to F-free. Then using F-free and T-clean, show that there is no highly connected set. And then using T-clean and no highly connected set, show bounded tree width. And so the first step will look not yet very connected to what we're about to do. It's due to Lawson and Rasgon, and they also used it, right? Remember, we saw at the beginning, if we exclude finitely many graphs, they told us exactly which ones to exclude. And this was one of the tools they used. And in fact, we're going to use a bunch of things that they used. They showed the following, and maybe the picture is slightly more helpful. If I have a bunch of disjoint finite size subgraphs of a graph, then one of three things happens. I get a big complete graph, I get a big complete bipartite graph, or I get a bunch of copies of whatever small graph I was looking at with no edges between them. And this is what these words say. If I don't contain a big complete graph and a big complete bipartite graph as an induced subgraph, and I have a large family of pairwise disjoint induced subgraphs, each of bounded size, then many of them pairwise don't have edges between them. And this is just, you can assume that all the graphs in S are in fact the same graph because there are only finitely many possibilities since they have at most P vertices. And then for every two, you ask what is the graph between them in a labeled sense. And you can do Ramsey on this and assume it's always the same graph. In this case, the graph is always a red edge at the top, and then this green edge from the third vertex of the first to the second vertex of the second. And so if your pattern of it's always this graph includes a horizontal edge, you get a big clique. And if instead you have some non-horizontal edge, you get a big complete bipartite graph. And if it includes no edge at all, you get a bunch of these graphs anti-complete. Right, so if we have a bunch of disjoint subgraphs and we're T-clean, which means we don't contain big complete and complete bipartite graphs, then a bunch of disjoint copies of something, in fact, give us a bunch of disjoint anti-complete, meaning no edges between them, copies of something. Which means that if we look at H, which is a bunch of copies of F, then getting a bunch of copies of F, in fact, gives us a bunch of copies of F with no edges between them, which is H. So in G, let's take a copy of F if it exists, remove it, take another, remove it, take another, remove it. And if we found 1,000,000 copies, then this Ramsey lemma of Lausanne and Rasgon tells us we get a copy of H. And if we don't get a bunch of copies, then at some point we stop because we've deleted a few vertices, but what remains is F free. And that's exactly what we wanted. Right? We greedily delete copies of F while they're there. We either find H or we stop in a few steps. And now the resulting graph is F free. So that's our first step done. For the next step, we're also going to proceed as Lausanne and Rasgon, and they showed the following, and I will try to convince you of a proof by only looking at pictures. Suppose, right, I told you a subdivision of a graph is obtained by replacing each edge by a path. And H is a proper subdivision of a graph if all paths have length at least 2, and a at most P subdivision of all paths have length at most P. Then what they showed is if you have a T clean graph, then we don't have short subdivisions of big complete graphs. And right, as subgraphs, we don't have big subdivisions, have short subdivisions of big complete graphs. And I mean, the reason kind of morally is because if we have a big complete graph and a short subdivision of it, we can Ramsey it repeatedly and either get a complete graph, a complete bipartite graph, or no edges between paths of the subdivision. And the more honest way to make this argument is if we have a short subdivision of a big complete graph, we have a short subdivision of a complete bipartite graph. And here are the two signs. We can assume each of these signs is stable by Ramseying, or we get a big clique. And now for each vertex here, I can look at the paths going to the other side and apply the lemma from the previous slide, which will tell us, in fact, we can assume that there are no edges between any of the rent bits for any given vertex. So for any vertex, the paths coming out of it to the other side have no edges between them, look induced. And now for each vertex here, I can look at this much, which is an induced subgraph of bounded size. And I can say for different vertices on the left, there are no edges between their corresponding subgraphs that look like the thing I've circled. Again, because these are bounded size, and now by the previous lemma, we can get a bunch of them with no edges between. And we have made this subdivision of a complete bipartite graph induced. And now we can Ramsey one last time, and either a bunch of the edges are not subdivided and we get a big complete graph, or a bunch of them are subdivided. And then one subdivision of a large complete bipartite graph contains a subdivision of any graph you want, in particular a big wall. Okay, so lots of Ramseying. But that tells us, right, just as the takeaway, we're happy if we find a short subdivision of a big complete graph, and then either you like Ramsey arguments, and then this is something you probably already knew or could figure out how to say, or you don't like Ramsey arguments and you accept that this is true. So we're now F-free, and we don't have a short subdivision of a big complete graph. And let's briefly go somewhere else and then see how to apply our short subdivision of a big complete graph result. A k-block in a graph, and this comes from subgraphs, but a k-block in a graph is a set of vertices of size k such that they are hard to separate, meaning G contains k internally disjoint paths between every two vertices in V. Right, so in other words, a k-block is a set of vertices such that for every two of them, you can't delete a few vertices and disconnect them from each other. And using our previous result, we're going to show that for every t, there's a k such that if we are t clean and f free, then there's no k block. Right, we've shown that we are in a setting where we're f free and t clean. And so this will just show that there's some k such that we have no k block. And how does it work? Here are the vertices in a k block, and we know that between every two, there are a lot of disjoint paths. So now let's do the following. If there are two such that I have a short path between them, let me pick such a path. Having deleted the internal vertices of that path, if there are any other two with a short path between them, let me also pick out that path. And we continue greedily. And in order for this argument to work, I'm going to actually pick a subset of the vertices in the k block. So I'll have a smaller set of vertices such that between them there are a humongous number of paths. But if there's a pair with a short path, I will pick it out, delete those vertices, and continue. And what happens when this stops? When this process stops, one thing that could have happened is that I've picked out a short path between every two of my vertices, in which case, from this, we're happy. That doesn't happen in a t-clean graph. Or I've stopped because there are two vertices and I don't have a short path between them anymore. Right, I took a k block. That means I have high connectivity between any two vertices. I've picked out short paths where I could, greedily in whichever order. If I found short paths everywhere, wonderful, because then we've got a short subdivision of a big complete graph and we win. And if I didn't, that means there are two vertices between which I don't have a short path. But it's a k block, so I still have a lot of paths between them. So here are two vertices between them, no short path, but I have a lot of disjoint paths, which means I've made this. And this is a subgraph, right? We don't know what's happening between those paths. There could be lots of edges. But I don't have a short path from x to y. And so for each of the red paths, I can take all shortcuts within the red path and use that instead, and that never hurts me. Which is to say, I can assume each red path is induced, right? Because if among the vertex set of this red path, there was an edge that makes it not induced, then I can remove some vertices from that red path and still have a path between x and y, and now it's shorter. So, right, from being in a k block, I get a lot of paths between them. From having stopped my procedure of pulling out short paths, I can assume all of these paths are long. And from taking shortcuts where possible, I can assume these paths are induced. And since there wasn't ever a short path, the induced paths are still long. which means if I just look at X's side of this picture, it looks like this, and right somewhere here in the distance is Y. And this thing looks very suspiciously like F, except I may still have edges between these paths. But then we look at all these paths and we apply the Ramsey lemma, and we get rid of edges between them. So right, we started with a K-block, we pulled out all these short paths between things. If we got that to make a big complete graph, right, a short subdivision of a big complete graph, we're happy, good things happen. If not, we found two far apart vertices with lots of paths between them. We pulled out this thing, which is F, except there are still some edges in certain places. We applied Ramsey to get F honestly induced for real, and a contradiction. So T-clean F-free graphs don't have a K-block. All right, so far we've not said much about 3D compositions in this proof, and here, I'm sorry, is the part where there will be 3D compositions. And we're going to say a few words about things in 3D compositions. In a 3D composition, we've already said a bang is just for a vertex in the tree, all the vertices in the graph that correspond to it. And an adhesion is the intersection of two bangs that are connected by an edge in the tree. So I'm going to point to the picture a lot now. Here's a graph, and the gray circles are the tree decomposition. And so here is the tree. It has four vertices, X, Y, Z, W. And here's beta of Y, beta of X, beta of Z, beta of W. Bangs are the gray circles, and then adhesions are the yellow highlighted parts. A torso is obtained from a bang by turning each adhesion into a clique. So if I look at this bang and I turn each yellow set into a clique, this is a torso where the colorful edges are exactly the ones that came from different adhesions. Right, these were in the same adhesion, they got turned into a clique. These three were in an adhesion, they are now a clique. Adhesion, clique. And one more technical thing, which I'm sorry, I tried very hard to find a way to say this without that, but we need it. In a 3D composition, each adhesion gives us a cut set, and a 3D composition is tight if for every two vertices in an adhesion, we have a path between them on the other side. So if we look at this adhesion, which corresponds to the edge from X to Z, and if I look at those two vertices, then I have a path between them, which doesn't go through the other side, meaning it doesn't go through the part of the 3D composition that's over here. And I'm being purposefully slightly vague. But this is a tight 3D composition for every two vertices in an adhesion. You can go between them in some sense on the other side, and that sense is in fact very weak, as this example shows. And so again, more stuff about 3D composition. So right, what we showed before is that there's no K-block, and what we want to use is this lovely theorem of Weissauer, who showed something about about graphs with no K-block. And for that, let me say one more lemma. If I have a graph and I just give you some 3D composition of it, good or not, the tree width of G is at most the maximum tree width of a torso, where remember a torso arises from a bang by turning adhesions into cliques. So even if I give you a terrible 3D composition of a graph G, the tree width of G is at most the maximum tree width of a torso. And then Weissauer's theorem says if we have a graph with no K-block, there is a 3D composition in which each torso is nice. specifically, then there is a tight tree decomposition in which every torso has only a few vertices of large degree, which is good news because we like it if all vertices have small degree by Korholen's result. And if only a few vertices have large degree, then let's delete them and then apply Korholen's result. Right, so let's briefly recap. If we showed there's no K-block, now there's a tight tree decomposition where we currently don't care what tight means, but we will in a second. And every torso has only a few vertices of larger degree. But also the tree width is at most the maximum tree width of a torso. So there is some torso whose tree width is at least the tree width of the whole graph G. In this torso, there are only a few vertices of large degree. Let's delete them, and the tree width of this torso is still pretty close to the tree width of G. But now also the maximum degree is bounded. So let's apply Korholen's result to this. It has large degree. I mean, it has bounded max degree, but it has large tree width. So we get an induced Wallard's line graph. And isn't that what we wanted? Right, we proved excluding H, we can clean up a little bit so that we have no K block. So we get this tree decomposition, we get a torso with large tree width, we delete the large degree vertices, we still have large tree width, max degree is bounded, Korholen's result gives us a Wallard's line graph. End of story. Except I've cheated you in one place, which is that in a torso we've added some edges. So a torso is not actually an induced subgraph of the graph we started with. So we are going to do one more slide to turn a Wallard's line graph that we found in this torso into a Wallard's line graph in the graph. And right, this is what I just told you. In this torso, we find a big Wallard's line graph. But there might be bits in our Wallard's line graph that look like this. There are edges that came from turning adhesions into cliques and not honest edges of G. And so what we're going to do with them is for each adhesion that intersects this Wallard's line graph, well, it only intersects it a little bit because walls or their line graphs don't have cliques of size more than 3. So from each adhesion, we have kept at most 3 vertices. And now if we've kept those 3 vertices, we know we can connect them on the other side of the adhesion, whatever that means. In particular, we can connect them in such a way that it doesn't mess with the rest of the Wallard's line graph that we've constructed. So let me go to the picture that hopefully tells you more about what happens. For each adhesion, we may have had these 3 vertices that were adjacent in the torso, but now let me instead just connect those 3 vertices on the other side of the adhesion. And so for each adhesion, I get somehow whatever subgraph I need to make, whatever induced subgraph I need to make to connect 3 things. And here are the 3 types of subgraphs I need to make to connect 3 things. And well, there's a few options, but kind of my main point is that they all have bounded degree. So we have this Wallard's line graph on the torso. We do a bit of modification relating to the torso not being an induced subgraph of G that turns this Wallard line graph into a graph that's very similar and now an induced subgraph of G, and it still has large tree width and it still has bounded degree. And so we hit it with Korholen's result one last time. It still has small degree, it still has large tree width. Let's just apply Korholen's result to this actual induced subgraph of G, and this now actually for real gets us a Wallard's line graph. And we could stop here since it's been exactly an hour, or I can talk for a few more minutes, entirely up to you.
So I'm okay with listening a few more minutes.
Okay, the few more minutes are entirely not proofs, so hopefully they will not upset anyone too much. We can make the star forest thing slightly stronger, and so we can actually promise instead of a star forest to get one of these things, which are right, the black part is a star forest, and then the red stuff connects that star forest in some way. And this uses a lovely result of Davies, which tells us something about if I have a connected graph and some vertices are special, can I find a connected subgraph which contains many special vertices but also has a nice structure? And essentially, the pictures you see here are the answers to this question in the case where we don't have large cliques. So we can get a little bit more and get these other connected things. And then my other slides are two kind of overview slides of, there are lots of different tree width results that exist. What do we know at this moment? The first is in which classes of graphs do T-clean graphs have bounded tree width? And we know not in all graphs by Cindiari and Trottignon's construction, but Korhonen proves in bounded degree graphs. In this talk, we saw in H-free graphs only for subdivided star forests. It's known for long hole-free graphs by Gartland Lokshanov, the two Polipchuk brothers, and Janjevsky, and also independently Weissauer. It's known in this class of graphs, which maybe I will not define in the interest of time. It's known in graphs where every vertex has at most one neighbor in a hole, which is sort of similar to excluding a wheel, but we're excluding a bit more. It's not true in even hole-free graphs. So this is my very brief overview of things that are known. And likewise, for many tree width results, logarithmic tree width, meaning tree width bounded by log number of vertices, is also useful for the dynamic programming and everything else. And logarithmic tree width might be more tractable because the constructions that are T-clean and have large tree width all have logarithmic tree width except for Davies's star grid construction that I showed you. And logarithmic tree width is known if we exclude 3-path configurations, and also if we don't have k pairwise disjoint anti-complete induced cycles. And I have a picture of their construction, the construction that shows logarithmic tree width is actually best possible for even no two induced cycles that have no edges between them. And it's quite pretty, right? You can now extrapolate. We give this one neighbor, we give this one neighbor, we give the next vertex one neighbor between every two attachments of previous vertices. This has 8 neighbors, one between every 2. It's just a pretty graph. I wanted to show it to you. That's all I wanted to say. Thank you, and please ask questions if you have them.